Well, I lost my voice. Hello and welcome to Thursday's edition of Cracking the Cryptic. Oh dear, that's not a good sign, is it? Well, we're going to be tackling this very colourful puzzle today called Parity Paradox by Marty Sears. I love Marty's puzzles. I was very jealous of the last Marty puzzle that appeared on the channel, which was not solved by me. The testers recommended that one for Mark. And I watched Mark's video and I was like, oh, that puzzle's amazing. I wish I'd got to do it. Well, luckily, I'm going to do this one today. So hopefully this will be something like that one in terms of sort of the sheer joy we'll be able to extract from the logic. I've read the rules. The rules aren't too long. I have no idea about the difficulty of this one. I forgot to look it up on Logic Masters Germany, if indeed it's there. So you might have to use the video length as a guide. Assuming, of course, I get through it with any sort of efficiency, which is by no means a certainty. Now, I've got some news for you today, though. I've got birthdays. I've also got to tell you that it's the last day of the month. Yes, we share these knowledge bombs on Cracking the Cryptic. But with it being the last day of the month, that means tomorrow is the 1st of September. And that means it is reward day if you're a patron of the channel over on Patreon. We have a brand new Sudoku hunt for you, of course. I think it's got 7 puzzles altogether. It's called Lines and Shapes, and it's because it portends the soon arrival of Line Sudoku, our brand new app. It's an app we've been working on for over a year, believe it or not. It just takes us a very long time because Mark and I test solve all the puzzles ourselves. We hint all the puzzles by hand, it takes a while. So anyway, it's coming very soon. It'll certainly be out in September, hopefully around the middle of September. And yeah, so we've got lines and shapes themed Sudoku hunt for you, and with a chance to win some brand new merchandise based around the hexagon shape of our logo. There you go. So if you like caps, that might be something you want to think about. Yeah, so that's coming tomorrow, 4 p.m. UK time. So check out your inboxes then. What else? Well, let's do some birthdays. Marcia, I know it was your birthday yesterday. You're a flautist, and I know this because you're the wife of Brennan, a very musical family. Brennan, of course, being responsible for our outro music. So if you ever listened to that and thought that sounds cool, well, Brennan composed it. Marcia, it was your birthday yesterday, but I know you've got COVID. There's a lot of COVID going around. Very unpleasant. I hope you feel better soon. I'm sorry if it ruined your birthday. And I hope puzzles like this one today can help you feel better. Next, Nadia. Nadia, it's your birthday today, and you're turning a secret age that I'd better not reveal. And you said it would make your birthday if I could recount the story of how the summation formula was discovered. Now, I'm not sure I know it, but I think you might be referring to Gauss. I don't even know when Gauss lived. I want to say 1750s. That could be total and utter rubbish. But I believe the story about that is that the teacher, I don't know how old Gauss was either, probably about 3 or something, and the teacher said, can you sum up the numbers 1 to 100? Something we have to do in Sudoku is to sum the numbers 1 to 9 occasionally. And Gauss was immediately able to come up with the answer of 5050. And the trick to doing that, of course, is that you don't go 1 plus 2 plus 3. That's going to take a very long time. You note that if you add up the extreme numbers, so if you add the 1 to 100, you get 101. If you add the 2 then to the 99, you get 101. And you keep doing that. And what you find is that you're going to have 101 times 50 as the answer. And 101 times 50 is a lot easier to do than 1 plus 2 plus 3 plus 4 plus 5, etc., etc. Actually, one way I heard that described before, which is quite appealing. If you imagine the list of numbers 1 plus 2 or 1, 2, 3, 4 in a line, and then you just reverse the line, so you have 100, 99, 98, and you put them one on top of the other, then clearly it's very easy to see that each pair of numbers adds up to 101, and you must have 100 such pairs, but you've now got 2 sequences. So it's, in effect, it becomes 101 times 100 divided by 2. Anyway, I'm no Gauss, as you've no doubt all noticed. But anyway, Nadia, I hope that is the story that you wanted me to tell. Probably butchered it completely. But anyway, happy birthday. I hope you have chocolate cake. Let me know if I butchered your story. Next, Mel and Jennifer, twins from South Carolina, whose mother, Rebecca, tells me they've now outgrown a valid sandwich clue. Well, a sandwich Sudoku clue maxes out, I think, at 35, because the numbers 1 and 9 have to sandwich things. So I think that Mel and Jennifer have turned 36 today. Happy birthday. I know Rebecca is a very proud mum. Jennifer's just earned her master's degree, and Mel has road tripped across the US, ocean to ocean, in the last year, not once, but twice. Good grief. So anyway, fantastic. Mel and Jennifer, happy birthday. And then final birthday is to Nicole over in Delaware, and that's from your boyfriend Dennis. And apparently Nicole goes for the party hats when doing the gas puzzles, which, well, frankly, we all do. And if you're not familiar with what the gas puzzles are, they are the genuinely approachable Sudokus that feature every day over on the Discord server. There's one every day, completely free, and they're fabulous little sort of coffee time teasers. And they should only take you, a few minutes, 5 to 10 minutes, especially as you get better at variant Sudoku. It's a fantastic way to improve your variant Sudoku skills. And Nicole is having ice cream cake today. Well, not chocolate cake, which I don't really approve of, but ice cream cake still sounds nice. Now, all that said and done, let's have a look at Marty Sears' puzzle. Parity Paradox, and we will read the rules. They are as follows. Normal Sudoku rules apply. Each line within a 3x3 box has the same total, which is displayed in yellow in that box. So what does that mean? So that means that, in fact, let's look at this box, because there are 2 lines in this box. So what we're being told is that, it does say 2-digit yellow totals read from left to right. So let's imagine this is 15. So I'll put 1 there and 5 there. What are we being told? We're being told that that line adds to 15, and that line, no, 15 isn't going to work. Actually, that's really, really not going to work because of a secret that I will share with you in a minute. I'll go up to 19. 19 might work. I don't know. Don't forgive me if that's not a valid example, but I think the way it works is that now you know that line adds up to 19 and that line adds up to 19. And okay, but that's not the end of the rules. Well, there's only one more rule. It says the digit in the purple square indicates how many of the yellow totals have the same parity, brackets oddness or evenness, so parity in a mathematical sense. Oh, as itself, hang on. How many, i.e. the purple square digit, right. So whatever, let's make that digit a 3. What are we being told then? We're being told that the yellow totals, of which there must be 9, because there are 9 Sudoku boxes, 3 of them have odd parity, is what we were being told, because 3 is odd. So if we change that to 4, 4 is even, so 4 of the yellows now would have even parity. If we change it to 5, then 5 of the yellows would have odd parity. 8 of them would have even parity. Yeah, okay, we understand that, I think. Do have a go at the puzzle. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. So this box catches my eye first. I'm not sure why. But I feel like I should be able to do some secretive mathematics on that box, which could be a totally not true. Actually, let me just think about this. Hang on a second. I've got a 7-cell line, which must add up to at least 28 because of Gauss. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. I guess we could do it the Gauss way. Gauss, well, yes, okay, because the summation formula is n times n plus 1 over 2. I do know that. So 7 times 8 is 56, divided by 2 is 28. So that's how we could do that if we didn't know the triangular number for 7. Okay, so 28. If that was 28, you're putting 2 and 8 here. And 2 and 8. Okay, yes, so we must be having to use the secret. So the secret is, and it's something I only tell my very favourite people, but of course I'm going to share that with you if you're still watching this video now. The secret is that any complete column, any complete row, and any complete 3x3 box of a Sudoku, by the rules of Sudoku, contains the digits 1 to 9 once each. And the digits 1 to 9, because I'm going to do it by Gauss again, 9 times 10 divided by 2, so 45. The digits 1 to 9 sum to 45. And that's the secret. So I know this box sums to 45. Now, and that allows me to disregard 28 as a possible total for the blue line, because this would be a 2, this would be an 8, and 28 plus 2 plus 8 is 38, which is not equal to 45. So that's wrong. But what we could do, yeah, okay, so if we express mathematically this number, we have to read it from left to right, but this is the tens digit, this is the units digit. So whatever this digit is, let's call it x, that's 10x. That counts as 10x in terms of the value of this line, doesn't it? So this line we could express, if this is x, let's make that x. I think I can do that with the line tool. That's x, that's y. So we can express this box as 10x plus y, that's the total of the line, plus x plus y. So the box overall adds up to 11x plus 2y. And that means x is 3, I think. Because if x was 2, 22, plus even if that was 9, 22 plus double 9 is not 45, it's only 40. So that has to be 3, because if it was 4, 44 plus 2y would require y to equal a half. So that's 3. There's probably a much simpler way of doing this. So that gives 11x. So we've got 33. Yes, so we've now got 2y is equal to the difference between 45 and 33, which is 12. So y is 6. Now let's see if that's total nonsense. Whether Gauss is turning in his grave. Okay, let me think. So we've got 30. Yeah, well, 36 plus 9 is 45. So I think that is, we have proof that. And that's rather pretty. I like that start. Okay, where do we look now? Should we try? We've got 2 single-digit yellow totals, but only 2. Do they all have to? Do all our totals have to be different? No, it doesn't say that. Okay. Well, okay, so what we could do here in this box, this has to be quite a mighty number, I'm going to claim. In fact, I thought about this very subject only recently. It might have been in Zeta Maths puzzle, but what's the minimum that those 5 digits can sum to? And the minimum would be 15. If I made them 1, 2, 3, 4, and 5, they would add up to 15. But there's 2 lines. So that means the absolute minimum value of this is 7.5, which is not a valid Sudoku digit. So that's got to be an 8 or a 9. And the same must be true. Exactly the same logic applies there. So if these do have to be different, they would have to be an 8-9 pair. Now, so if it was 8 here, these would add up to 16. So they would have to be 1, 2, 3, 4, 6. I'm just wondering if we could disprove that. Can we disprove that these 5 cells in both boxes can be 1, 2, 3, 4, 6, which is the only way of making 5 different digits add up to 16. 2, 3, 1, 2, 3, 4. Don't think so. Okay, maybe I'm not looking in the right place then. We've got an 8 cell line in this box. So, okay, so that's telling me... Can we do our maths again? Can we do algebra again on this? I think we probably can. I'm not sure. Let's try. Hang on. We'll make that x and that y. Now, what are we saying this time? So this line's total is equal to 10x plus y. Okay. Oh, yes, well, that is a lovely way of doing it, actually. So the box's total, if the line's total is 10x plus y, and the box's total just includes that cell again. So the box total here is 11x plus y. Now, this time, if we made x equal to 3, we'd have 33, and then y would have to equal 12. Well, that's too big. So this time, x is 4. It certainly can't be 5, because 55 is bigger than 45. So this is 44's worth of 11x here, so that's got to be a 1. Now, again, I'm sort of suspicious of doing the maths this way. Normally in Sudoku, we sort of iterate and feel around the subject, don't we? But this is the units digit. So if the line adds up to 41... those squares then add up to 40. Yeah, that's lovely. Those add up to 40 because, you know, this digit here is sort of, it's in the 41 sum and it's on the line. So the other digits add up to 40, and 40 plus 4 plus 1 is 45. So that works very, very cutely. Okay. So I'm tempted now to try. Can we do this one? This has got 2 digits on a line. So what are we being told here? So this line's total, this smile total. But that... Oh, I can do this, you know. I can. I really like this. It's like you have to do a little puzzle in every box so far, and they're all a little bit different. Okay, so this one, the way I'm thinking about this one is that this digit, whatever it is, let's imagine that this was, I don't know, 16. Let's just put 16 in. What I can see is happening here is that now I'm saying that those 5 digits add up to 16, but this is the tens digit. So that tens digit, being a 1 in this case, would be saying that those 4 digits add up to 10, because this is counted. It's counted in on both sides of the equation, isn't it? It's the units digit of the yellow, but it's also in the blue, if you see what I mean. So if this was a 2, we'd be saying those 4 digits have to add up to 20. Now, the interesting thing about that is that this line can't add up to 20 anything. The maximum they could add up to would be 8 and 9 is 17. So that digit is a 1, which means these digits... Hang on, I'm going to get this wrong now, am I? No, they have to be 1, 2, 3 and 4, yeah. Because these... So what we're being told now is whatever this digit is, these 4 digits add up to 10. The other digits on the line, because that's what this digit is. So the only way of making 4 different digits add up to 10 is with 1, 2, 3, 4. So that's 1 and 4 must go in those 2 squares. These squares must be 2 and 3. And we still haven't got a Scooby-Doo what this number is, except it's not now 1, 2, 3 or 4. So the least it is 5. And then these would have to add up to 15. So, okay, that's got to be then 5, 6 or 7. Because I can't make this add up to more than 17. Ah, this is cute. Oh, and 1s and 4s now have to be... Sorry, I'm in letter mode. 1s and 4s have to be over here. And we've got... this one looks horrible, though, doesn't it? Because that digit is on a different line to this digit. This... Although, does that have to be a 1 now I think about it? If this was a 2, we'd be saying that this line now has to add up to 20-something. Whatever this is, that line has to add up to it. And 20 is not a possible total on a 3-cell line if one of the digits on the line is a 2. So that is a 1. Aha! Aha! So this is a 1. Okay, so... Oh, this is... Oh, that's exquisite. That is exquisite. So I now know what those 3 digits are, I think. And that, again, it's the same sort of logic. This number, if we imagine, well, the way to do this puzzle is to imagine on one side of an equation, you have the yellow total, and on the other side of the equation, you have the blue cells. Now, this digit is in the yellow total. It's the units digit on the yellow, so it's in that side, and it's also on the blue line, so it's on that side. So they cancel out of the equation, and we're being told here that therefore 1 times 10, which is 10, is equal to the sum of those 3 digits, which don't include a 1. And the only way of making 3 digits add up to 10 without including a 1 is with 2, 3, and 5. So we keep being able to use the tens digit without having a clue about what the units digit in yellow actually is. So here, if that was an 8, 7, 8, 9, that would be 18. That would have no. So it couldn't be an 8, 9 pair here. That would require another 8. Might only be possible. That digit might be quite restricted, actually. Let me just think about this. If it's 4, we're saying these 14 is the total for this, so these add up to 13. Even that's quite difficult. That would have to be a 6, 7 pair. If this is 6, which is the next lowest it could be, then these have to add up to 15. They could be a 7, 8 pair. Oh, it can't be 6. It can't be 6 by Sudoku of all things. Outrageous, Marty, to make me do Sudoku in your Sudoku puzzle. Right, let's try 7. So 7 is 17. That requires these to add up to 16. But that requires a 7, I think. That would require those to be a 7, 9 pair. That doesn't feel like it works to me. And 8, I think I just disproved, because 18 here requires these to be an 8, 9 pair, which also doesn't work. So that is a 4, believe it or not. That is a 4, and these 2 squares have to add up to 13 without using 4, 9 or 5, 8, so they're a 6, 7 pair. And whoopsie, so these digits are an 8, 9 pair, and we've got an 8, 9 pair in column 9 out of nowhere. We can get rid of 3 from this cell by our old friend Sudoku. 2, 2, 3, looking at that square, so that's a 5, that's a 2, that's a 3. No 3 in the corner in the bottom row. Could still have a 3 in the corner here, could have one here. We need to put 1, 2, 3, and 7 into this column, which might matter. Don't know. I mean, I can see that there are some digits that I probably have to have on these blue lines in order to keep them adding up to no more than 18. I mean, they're going to have 1s on them, because 2, 3, 4, 5, and 6 add up to 20. And the way I know things like that is because I've learnt over the years what the triangular number for 6 is. I know it's 21. So I know if I miss out a 1 from that sequence, I'm going to have the sort of minimum total of 5 digits, which is going to be 20, which is higher than 18. Blah, blah, blah. I feel like I'm wittering. Don't witter, Simon. Okay. So there's going to be a 1 on there. There's going to be a 2 on there by that logic. But I don't think we know. There's not enough 1s and 2s pointing at box 3 to be sure. Does there have to be a 3 on there? Because that would then have to go there. And the answer is no. Well, there would have to be a 3 on there if this was an 8. But 4, 5, 6, 1, and 2 add up to 18, don't they? So we can get to 18 without a 3. Bobbins. All right, let's try this one maybe. Does that work the same as this one? Yes. Well, it does for that digit. That's got to be a 1, because again, if this was a 2, we'd be saying those 3 digits added up to 20 something, and one of the digits would be a 2. So that's not going to work. So now we're being told, oh, so this is a 9. This is going to be massive. This is going to be massive. Yeah, because what we know is that this is the units total for the value of the blue things. So we can cancel that one out from both sides of our equation, and 10, which is effectively the value of this digit, is equal to the sum of those two squares, one of which therefore must be a 9. So that's 8. Oh, we don't know if these are different. I keep coming back to that thought. 8, 9 here. So now, all right, now these digits do have to have 3 in them, because we know that they've only got one constitution. 5 digits adding up to 16 must be 1, 2, 3, 4, and 6. So we know that this is the 3. We've got a 2-cell line that has to add up to 8. Well, that's got to be 2, 6, hasn't it? Because it can't involve a 4, because it would have to involve another 4 if it did. So we get a 1, 4 pair, which actually is resolved by Sudoku of all things. We get a 2, 6 pair. We get box 9 is finished, which is quite surprising. I don't think the top. Oh no, that digit's known. I think that's a naked single. Because this box has not had 5, 7, and 9 put into it, and that seems to see 5 and 9, so that becomes 7. There's a 5, 9 pair left to place. And these two squares are a 1, 2 pair. And yet again, the units digit lets itself down by being unknowable. So if this was 8, we know that this would be 2, 6, do we? I think that must be true. So this would have to be, this is always 2, 6, this is 1, 3, 4. Which doesn't work. Right, so that is 9, that is different. Because if this was 8, this 3-cell line has to be 1, 3, 4. And the 1 and the 3 would be Schrödingered. They'd have to be simultaneously in row 2, column 5. So that doesn't do, it's simply impossible. So that's 9, that's 5. So this column has not had 8 or 9 in it. We can put those in. Whoopsie, I didn't mean to do that. Lost my army. This is 4, 5, and 7, I think, which looks good from the column perspective. These digits now add up to 18, which is probably useful. Well, let's think about that one, because this one adds up to 9, doesn't it? And it's not 1, 3, 5, because this square would be Schrödingered again. It's not 1, 2, 6, because that square would still be Schrödinger, 1 and 6. So this is 2, 3, 4. There's a 2, 4. This is lovely. That's a 3. This is a 2, 4 pair. This adds up to 9 without using 2, 7, 3, 6, or 4, 5. So that's 1, 8, and we know the order. Oh, this is gorgeous. 1, 2, 3, 4, 5, 6, 7 into these squares. So that's a 6. This is a 5, 7 pair. Let me mull 5. So this is 5, 7, or 8 now by Sudoku. Now, does that make this line, or maybe those two digits, difficult? I have not got a clue. Let's think. So the maximum size of these digits is quite an interesting question. Because, this is a 2, 3, 4 triple. So that digit's very low. 10, 15, 15, 30. Right, we can get rid of 5 from this square. If this is 5, that line adds up to 15, so these 7 squares add up to 30, and these 2 squares would have to add up to 15. That's not possible. If one of them's a 2, 3, or a 4, that would have to be at least 11. So that's not 5. If this is 7, we've got 17, 34, so these are adding up to 11. Oh, it's nearly impossible. That would only be possible if that's a 4 and that's a 7. Because 2, 9 and 3, 8 both break in the row. So 4, 7. Hang on, did I just say that was 7 to make that happen? I think I did. If that's 7, 17, 34. Yeah, there's no way. You can't make that domino work. So this is 8, is what we've just learnt. took me a while to get to see it, but okay. So now this is 36 for these. These add up to 9. So this square is 7, 6, or 5. That's unbelievable. 7, 6, or 5, all of which are totally possible, apparently. Okay, sorry, that was not how to do that. That's not 6, because 6 in this row is definitely in this domino. It's 5, 7 pair in row 3. Oh dear. Okay, so we're going to have to look for something else. And I don't think I fancy that one very much. I think let's have a look at this one. Can we do something with this one? Oh, well, one thing we can do with this one straight away is that number can't be a 1. So it's a 2. It just is a 2. Because what we're saying, if this was 3, we'd be saying this adds up to 30-something and that adds up to 30-something, and the box would add up to 60-something, and we know the whole box adds up to 45. So that must be a 2, and that's got to be quite a low number, I think. Although, actually, well, that can't be 1. Yeah, that's got to be 1. Because if this wasn't 21, which means those 8 squares are summing to 42, if this is any higher, this has to be too low a digit, and it can't be 1 or 2. So that's got to be 1. I think that's got to be 3 to make the box add up. Then we've got 21 on that line, 21 on that line, and 3 gives us 45. So now I've got a 4 here, look. Which means we know these add up to 9, wasn't it? I think it was. So we can take 5 out now. We've still got the 3 in the corner possibility. We've got a 2, 3 pair in this column. Oh, let's have a look at column 3 actually, because I'm seeing we've got a 2, 3 pair in there. So these squares are 5s, 6s, and 7s. Let's put that in. And this has to add up. These 3 squares have to add up to 20, don't they? So, oh no, it's not quite forced. I thought it was going to be forced, but it isn't. I mean, if that's a 5, 6 pair, that's got to be a 9. If this is a 6, 7 pair, that couldn't exist. It would have to be 7. So this is an 8 or a 9, which does give us a pair in row 6. Look. Bobbins. I don't know how to do this. Oh, you know what? In this row, I've got a 2, 3 pair, and I've got 5 other digits. So these 2 squares are quite restricted. Not restricted enough, but quite restricted. Can we do anything with that? What about... We know that this line is adding up to 15, 16, or 17. So if this... I think there might have to be a 9 on this line. Because if it's 15, that's got to be a 6, 9 pair. And we'd know the order. If it's 16, we need that to be 9, 7. And if it's 17, we need it to be 9, 8. So there is always a 9 on this line. I'm trying to see what that does, and I can't. Oh, bother. I know what we're going to have to do. We're going to have a look, I think, at the middle box. So what are we being told in the middle box? We are told that this line sums to a 2-digit total. So it's probable that this is a 1, isn't it? But it could perhaps be a 2. If it's a 2, it's a 1 or a 2, because this can't add up to 30-something. If it's a 2, I suppose it could be like 7, 8, 9, adding up to 24 or something. Actually, it could well be. We're seeing a lot of low digits looking at these squares. That square is at least a 5. Right, so there's a 1, 2 pair in row 4, look. I feel like I'm getting stuck here. I don't want to get stuck. It's been very smooth to this point and absolutely gorgeous. And now I have to think harder, don't I? 3 in the middle box is nearly in the purpley thing, which would be a very handy deduction. Is there some way... that digit's not a 6. So, oh, I see, yeah, that we can do Sudoku. Where's 6 in this box? The answer is, I don't know. But it's definitely, oh, whoopsie. It's definitely in one of these 2 squares by Sudoku. So it's looking up at that square. So that's got to be 7. Which means that's got to be 2, because we worked out those had to add up to 9. No, it's not a 2 in the corner. No, 3's in the corner. Okay, well, that's fine. This is now 5. This is 6. So this is 5. This is 7. We've done a little bit more Sudoku there, and that 7 is ruling a 7 out of this square, which might matter. 6 is definitely on the line in this column. So what do we know? We know we've got 21, so we know these are adding up to 20 and they have a 6 on them. So so the other 2 digits have to add up to 14 without using 6. So they can't be 6 and 8, so they must be 5 and 9. Right, that's perfect. So now we can take 7 off this line and we can add 9 to it, and that's become a 6. I think I said that this line always had to have a 9 on it. So let's check that. 15, yeah, that's giving us 15 here. 5, 6 means that's a 7. That's got to be an 8 by our old friend Sudoku. That digit's now a 9. And we can get rid of the 6 corner mark here. Oh, whoopsie, I'll keep misclicking. And we've got 4, 7 and 8 down column 1. And oh, this 9 is seeing some things. 9 here, 8 here. So this is not 8. And these squares are 2, 3, a 2, 3, 5 triple. And that's not 5 and that's not 3. So these squares have got to be 5, 6, no, 6, 7 and 8. That's an 8, forced. And that 8 means, oh, we've almost got an 8. Sorry, we've almost got an 8 in this cell. Oh, but there's no 8 on this line now. Oh, look, well, there are 4 9s looking at the middle box. If I double click the 9s, you can see there are 4 9s looking at the middle box. Well, when you have 4 of a digit looking at a 3 by 3 box in Sudoku, you can always place that digit. So can we get to 20 now? Yeah, we can actually. 7 and 6. Although we couldn't have, that can't be 22, can it? Oh, it can't be 21 now because of this 1. Yeah, so we have got a problem with this. I think this is a 1. Because if this was a 2, what are the actual options for it to exist? We can't put 8 on the line. So the highest we can get to is 22 with 9, 6, 7. 22 is not a valid option here because it would repeat the 2. So we have to go 21, which doesn't work. So this has to be a 1, which means that's a 1 and that's a 2. And now, so now we're pushing this digit up again, aren't we? That's probably what's going to happen. Whoa, what's going on in column 5? We need 2 and 5 into that square. Um, 18, is 18 difficult for some reason? These would add up to 9. That couldn't be 3 then, because that would plonk a 6 here. But that could be 4, 5, and 2, 7, and think. So that's still a little unrestricted. So I'm not quite seeing how to finish this off. I've not. I'll tell you one thing I haven't thought about, and that's that purpley thing. What was the purpley thing? How many of the yellow totals have the same parity as whatever this is. Right, so what's the parity count? That's even. That's even. We don't know what this one is. That's even. That's even. So we've got 1, 2, 3. We've got at least 4 evens. So if this was a 5th even, that couldn't exist, could it? What would you put in that square? Am I going mad? I don't think that square could exist. If that was even, we'd have to put 5... I suppose, yeah, we'd either have to have that as indicating 4 odds. Well, the thing is that 4 is not an odd number, or 5 evens. It's a paradox. It's a paradox. It's a paradox. That's what it is. It's a parity paradox. Sorry, Marty. I didn't have a clue what was going on until I've just almost said the title of the puzzle. Bobbins. Okay, right. But what we've just learned is that is not even. So it's certainly not 8. So that seems to place the 8. Okay, that's very clever and very funny. So now this square is, 4, 5 or 7. And this has to be odd. So this is 3 or 7, isn't it? We've just worked out it can't be even. And I think it sees 1, 3, 9 and 5. So it must be the other odd number. And that gives us 7 at the bottom and 6 here. So that means this isn't 7. So this is 4, 5 or 6. So now we've got 4 even yellowses, and we must have 5 odd yellowses. 1, 2, 3, 4. Oh, hang on, I've miscounted. No, 5. There we go. 5 odd yellowses, 4 even yellowses. So this number is not 3. That's certainly true. So that must be 3. And now we can do the maths to make this work. So we've got 12, we need 17, so that's 5. Which means that's 2, that's 5. This is 2, this is 3, this is 2, this is 4. Now, is this done now? Hopefully. That's not 5. This is 4 or... Well, no, it must be 4 then. Because it's either counting the odd numbers of yellows, which is 5, or it's counting the even numbers of evens, which is 4. So it can't be 5, so it is 4. That's 4, that's 7. 4, 7, that's 5, that's 6, that's 5. That's 4, that's 7, that's 6. And hopefully 2 and 3 go into the grid. And that might be the correct puzzle. Congratulations, you successfully avoided a parity paradox only just and solved the puzzle. That was gorgeous. 83 people in 17 days. So the Gausses among you will instantly be able to say that that's about 5 a day, isn't it? Something like that. Probably not. I hope I've just embarrassed myself again. I love that. That was very cool. What I think this has... What I particularly liked was the fact that it felt like every box had a different puzzle in it. Although there were a few puzzles a few months ago that had that feature. I'm trying to remember who set them now, but they all had a little arithmetic trick that you had to do in each individual box, and this felt along the same lines. It was probably Marty's puzzle. I can't remember. Yeah, it was really, really lovely, and that's quite a mathsy episode, isn't it? There wasn't any. We weren't doing differentiation and integration, but we did a bit of algebra today, which makes a nice change. So let me know in the comments if you enjoyed the puzzle. I hope you did, and I enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.